Here is a combined summary of the 4 pages. Decentralized artificial intelligence systems face critical data security and privacy concerns, particularly in healthcare and finance domains. Researchers from Nesa address this by developing a comprehensive security framework that leverages multiple techniques, including zero-knowledge proofs, consensus-based verification checks, split learning, and hardware-based trusted execution environments. The primary aim is to enable the secure democratization of AI through scalable, high-security frameworks tailored for distributed environments. The security approach focuses on mitigating data security and privacy issues specific to distributed inference, balancing robust protection and performance efficiency. 2 critical scenarios are addressed: critical inference, which demands strict protection for applications like medical diagnoses and high-value transactions, and general inference, which involves less demanding environments. In critical inference, zero-knowledge machine learning and homomorphic encryption are applied strategically through techniques like ZKDPS and sequential vector encryption to maintain accuracy and data security. In general inference, Nesa's verification methodologies via CBV ensure faster task handling within high confidence rates. The security flowchart in Figure 1 illustrates the orchestration of user data, AI models, and node runners, ensuring secure data and model transmission via SHI and ZKDPS for model verification. Table 1 summarizes the proposed security and privacy solutions, categorized into critical and general inference scenarios. Nesa's ZKDPS ensures model verification and integrity, allowing one party to prove to another that a statement is true without revealing any information beyond the validity of the statement itself. For data privacy, sequential vector encryption is proposed, enabling computations on encrypted data without decryption. The paper highlights the importance of defending against adversarial attacks in decentralized AI inference environments and introduces new techniques to speed up the ZK process, ensuring the security of foundation model inference without compromising performance. Decentralized machine learning protocols utilize zero-knowledge proofs to ensure the honesty of parties executing inference protocols for foundation models. This involves a prover demonstrating successful execution without revealing confidential information, or the witness. Zero-knowledge proofs possess completeness, special soundness, and zero-knowledge properties, guaranteeing that the proof will pass verification only if the prover is honest while maintaining witness secrecy. These proofs can be classified as interactive or non-interactive, depending on the verification process. Interactive proofs involve the verifier sending challenges to the prover, who responds, and the process repeats. Non-interactive proofs use a random oracle model or hash function to simulate the verifier's challenge. In the context of Nesa's products, zero-knowledge proofs are applied to ensure accurate execution of computations on foundation models by computing nodes. The prover uses the generalized Peterson commitment scheme to commit to witness data and generates a proof of execution, which is transmitted to the central server for verification. A semi-dishonest assumption is made on the central server, which aggregates results and reports verification outcomes honestly but tries to glean additional information. However, some computing nodes might be dishonest, substituting their model or outputting random data. Assuming a majority of nodes are honest, the protocol remains secure. The paper discusses a cryptographic protocol based on the Peterson commitment, enabling the prover to prove knowledge of witnesses S and T without revealing them. The prover sends commitments of S and T, and the verifier sends a challenge E. The prover computes S and RT, and sends them back to the verifier, who checks for consistency. This protocol uses multilinear extension for zero-knowledge proofs of arithmetic operations, enabling the verification of arithmetic operations between vectors to be equivalent to the verification of the sum of multivariable, low-degree polynomials. The sum check protocol, also known as the GKR protocol, is employed for verifying the execution of linear layers in foundation models. This interactive protocol involves multiple rounds, with the prover sending a polynomial to the verifier, who checks if the equation holds. If it does, the verifier samples a random number and sends it to the prover for the next round. This process continues until the final round, where the verifier checks if the polynomial matches the opening of the commitment by a proof system. To reduce linear layers to the sum check protocol, Linear layers can be represented as matrix multiplication, and the ReLU activation function can be reduced to bit decomposition. This decomposition allows for the application of the sum check protocol to verify the execution of ReLU activation layers. Lookup tables are also used as a technique for zero-knowledge proofs of non-arithmetic operations. The prover commits to a table of values and the verifier queries the table at a random index. The prover then needs to prove that the queried value matches the actual computation result using the sum check protocol. The integration of these techniques enables the construction of zero-knowledge proof systems for foundation models, comprising transformer layers and MLP layers. Arithmetic operations in linear layers and MLPs are proved using the sum check protocol, while non-arithmetic operations, such as softmax and SWI-GLUE, are proved using lookup tables, and ReLU operations are proved using bit decomposition. Table 2 lists the zero-knowledge proof techniques for various operations in foundation models, highlighting the need for carefully designed techniques for efficiency. Notably, ZKLLM is the first work to introduce zero-knowledge proofs to foundation models with tens of billions of parameters. The ZKDPS system, built upon ZKLLM and ZKDL, aims to accelerate proof generation for decentralized large language models. Sequential vector encryption, SVE, is also introduced as a robust encryption method, focusing on select linear layers in modern LLM architecture. Secure vector execution, SVE, is a technique designed to obfuscate the output of every operator in a sequence of large language models, LLMs, to prevent sensitive information extraction. SVE involves randomly transforming the outputs of every operator, making it difficult to interpret the intermediate vector representations. For linear operators, transformation can be achieved through a product of invertible transformation matrices and the original matrix representation. For nonlinear operators, such as the ReLU operator, symmetries can be exploited, and a random vector with positive entries can be scaled to further obscure the transformation. To maintain security, secret sharing is employed to obfuscate the transformation matrices. In general inference scenarios, a consensus-based verification check, CBV, is proposed to ensure model verification and integrity. This approach leverages the collective agreement of multiple nodes to ensure correctness and integrity of model execution without revealing sensitive data. Split learning, SL, is employed to maintain data privacy by dividing the model into segments, each trained on different nodes. In decentralized machine learning, the Nesa framework employs a consensus-based verification approach to ensure the integrity of model execution across multiple nodes. This methodology involves redundant execution, output collection, consensus determination, and verification. For model sharding, Nesa adapts the consensus-based verification approach to accommodate the fragmented nature of model execution. The consensus-based distribution verification (CDV) strategy assesses the statistical distribution of model outputs across the decentralized network, evaluating the aggregated statistical characteristics of the outputs using metrics such as mean, standard deviation, and higher-order moments. The CDV process involves sharded execution and output synthesis, followed by advanced statistical aggregation and rigorous distribution comparison. This approach enhances security and privacy without direct comparison of individual inference results, ensuring the integrity of the complete model execution. Nesa's decentralized framework for large language models necessitates robust integrity verification and data privacy measures. The proposed consensus-driven verification (CDV) mechanism employs adaptive thresholding, leveraging differential privacy methods to enhance model security and maintain stringent privacy standards. This approach focuses on distributional characteristics rather than discrete output values, aligning with the goals of enhancing model security and maintaining data privacy. To address data encryption complexities, Nesa utilizes split learning (SL), partitioning the computational model to process data in parts without revealing sensitive information. Trusted execution environments (TEs) provide a hardware-based solution for secure and private computations, protecting users' input data and private model parameters. Nesa designs a specialized version of TEs, named NTEE, suitable for decentralized inference scenarios. Ts offer isolated execution, data privacy, and consistency and integrity, ensuring secure computations and data protection. The advantages of Ts include isolated execution, data encryption, and attestation, allowing nodes to trust results without accessing actual data or model details. Nesa's implementation of NTEE involves initializing a blank virtual machine T to each node runner, followed by remote attestation and secure transmission of user data and AI model fragments. The NTEE paradigm enables scalable and secure collaboration among multiple nodes, allowing them to pool their data securely for training and inference while maintaining data privacy and compliance. Figure 5 illustrates the high-level overview of the process, showcasing the secure transmission of data and AI model fragments, execution of AI inferences within Ts, and destruction of Ts after inference tasks to prevent residual data leakage or unauthorized access. Nesa's decentralized AI system leverages trusted execution environments, Ts, to ensure confidentiality and integrity of user data and AI models throughout the computation lifecycle. The system involves multiple Ts across various nodes, requiring advanced strategies for efficiency and security. In Step 4, each node runner's T performs a part of AI inference using the model fragment MI on data X, providing an isolated environment for secure computation, denoted as Y equals MI, X. For sequential tasks, the orchestrator sets up encrypted channels among nodes with computation dependencies, allowing direct transmission of intermediate inference results. In Step 5, the final inference results YK are securely transmitted back to the orchestrator from the last node's T using an encrypted channel like SSH. After successful retrieval and verification, the T on the node runner is destroyed, ensuring removal of residual data or model information. Nesa's innovation in Ts involves communication optimization among multiple Ts, establishing preset secure communication channels to minimize data transfer between the orchestrator and each T, reducing latency and improving overall system efficiency. Direct communication between Ts is secured using encrypted channels, ensuring data privacy and integrity during transit. A key exchange protocol, such as Diffie-Hellman, is employed to generate a shared secret key, from which a session key is derived using a key derivation function, KDF, for encrypting data transmitted between Ts. Nesa's heterogeneous T scheduling strategy involves dynamic scheduling based on initial attestation results, determining whether a node supports GPU-T or CPU-T only, leveraging the strengths of each type of T to optimize overall system performance. The system ensures efficient and secure performance across heterogeneous Ts, minimizing delays and maximizing resource utilization, enabling seamless scalability without compromising performance or security. The authors draw upon existing research to inform their approach to privacy-preserving training of encrypted data using split learning, referencing works by Tanveer Khan et al. 29, Hugo Touvron et al. 30, Cynthia Dwork, 31, and Ruzba Benia et al. 32. They acknowledge the concept of differential privacy, introduced by Cynthia Dwork, 31, and the development of trusted execution environments, Ts, on GPUs, such as Graviton, 33. The authors also draw on the foundational work of Ralph C. Merkle on secure communications over insecure channels, 35. Their approach involves using split learning to enable the training of encrypted data while maintaining data privacy through a combination of techniques, including differential privacy and Ts. This provides a more secure and private alternative to traditional machine learning methods, which often rely on sharing sensitive data. The authors present a framework for privately fine-tuning large language models, building on the work of Ruzba Benia et al. 32, utilizing differential privacy to ensure the fine-tuning process does not compromise data privacy. The use of Ts, such as Graviton, 33, is proposed as an additional layer of security and privacy for the training process. The authors argue that combining split learning, differential privacy, and Ts provides a robust and secure approach to privacy-preserving training of encrypted data. This approach enables the training of encrypted data while maintaining data privacy, providing a secure alternative to traditional machine learning methods. The author's framework for privately fine-tuning large language models and the use of TEs provide a comprehensive solution for secure and private machine learning.